So in this video we're going to calculate mean, which we'll have to do anyway, but you should have had a lesson on that already, and standard deviation. So we want to be able to calculate standard deviation from a list of numbers, for a frequency table and for a grouped frequency table, just like you've calculated the mean for those three types of representation of data. So what is standard deviation? Well, if the mean is a measure of where the data is, so the location of the data, then standard deviation is a way of measuring how spread out the data is. And it says here, why do we do what we do to calculate it? Let's say you've got a set of data, and the set of data is, let's have 5, 5, 5, 5, predict it, 5. Okay, then you can see from that the mean of the data is simply 5. And if we're to think about, if that is the number 5 there, think about how the data in the list differs from the mean. We can see it doesn't at all. So all of those bits of data are actually here. So we'd want a measure of spread that would represent that. Okay, so let's think about that. What we could do is we could say, well, okay, I'm just going to find out how far away the values are from the mean. So let's try 5 minus the mean, 0. 5 minus the mean, 0. 5 minus the mean, 0, etc. And say, well, okay, the average of those values is 0. That seems to work. Let's try it with another set of data. Let's try 6, 4, 7, 3, 5. Seems reasonable. Okay, so let's do it first of all thinking about how far the data is from the mean again. So the mean for that data is again going to be 5. This time we've got one number that's 1 above, a number that's 1 below, a number that's 2 above, 2 below, sounds almost like that should be a group, and 5, slap bang the same as the mean. So if we were to think about that as being a positive difference and that as a negative difference, then we would say that the difference away from the mean, that's 1 above, 1 below, 2 above, 2 below, can't get over that one, and the same. And if we add those all up, then we would say, okay, average distance from the mean is also 0. That doesn't help. So what we do is we say, well, okay, what we're going to do is we're going to square the differences. So if we look at the 5, 5, 5 list, if we want to square the differences, then what we would have is, if I draw a line there, it might be easiest. Square the differences, it's relatively easy to see that we will still have 0 squared plus 0 squared plus 0 squared, still 0, so it's still a small variance, whereas for this data here, that was the 5, 5, 5, 5, 5. This data here, if we now square the differences, excuse me, we now have 1 plus 1 plus 4 plus 4 plus 0 And if we find the average of the squares of the differences, then we get 5 plus 5 is 10, 10 divided by 5 is 2. And it makes sense that this should be represented by something other than 0 because they are away from the mean. If you were to look at values that were even further away from the mean, so you could try this yourselves, if you thought about having values like, let's have 5 plus 10, so 15 and 0, and put 7 and 3 and 5 again, you should find that the variance again increases. Now, that word variance is important because that's actually what this calculation is called. It's called variance. Statistically, it's called variance, and it's measured using sigma, the Greek symbol, squared. Okay? If we want to get standard deviation, we just square root the variance. So to get standard deviation, we square root this value. So the formulae for standard deviation are here. The plural has been put in brackets, I'll explain why. You've got one calculation here. This is what we did, we found the differences from the mean, squared them, and divided by n, and that was for the variance. When you square root, you get standard deviation. This formula here is an equivalent formula. It gets you exactly the same values, the same calculation value, but it is usually more efficient. The second formula is exactly the same as the first, but for a frequency table. So all it's telling you to do is find the differences of the data value from the mean, square it, and then say how many have I got? Well, I need to add them all up by multiplying by the frequency. And then you divide by the total number of values, which is the total frequency. Not to be confused with the frequency of that particular data value. Okay? Similarly here, the formula for a frequency table, and we'll see it in practice, so hopefully it'll make more sense. So the first example, example 1, I like to call my first example example 1. It's traditional, but it works. So, we've got a choice of formula. And if the mean turns out to be a really lovely number, and we have quite a bit of time, it's worth actually thinking about using this formula. If you've got a spreadsheet especially, it's quite a nice formula to use. However, this is the formula that I would always recommend you use because, as I say, you are less likely to make an error. You're not finding lots and lots of differences, you just have 3 different statistics that you need to calculate, different values to calculate. So the first one you need to know is the number of numbers, n. The second one you need to know is the sum of all the x's, which is the same as you would need for the mean. The third value, you can see here, is the sum of the x squareds, which is asking you to square each of your values and then add them all together. So for n, just getting a calculator. So for n, we've got 1, 2, 3, 4, 5, 6 bits of data. Sum of the x's, 2 plus 2 plus ... plus 20. If I use a calculator to work that out, I get 57. And then the sum of the x squareds, it's the same as the sum of the x's, only different because it's x squared being added to x squared, so we have to square each of these. And we get 893. Check along with me, make sure you're getting this, write the examples down, and if you're not getting the same values, you need to let me know, because I might have made a mistake. And so we can just substitute these into the formula. So standard deviation is equal to the sum of the x squareds over n minus the sum of the x's over n, all squared. You might have noticed that this part of the formula is actually just x bar. Be careful writing that, because if you do write it as x bar and the value that you get for x bar isn't a whole number or isn't an easy a terminating decimal, then you will find that you might substitute a value that isn't entirely correct, so you get a knock-on effect with errors, okay? So I would always advise putting the actual values there. And if we work that out, so you should be working it out at the same time, then we should have the square root of 58.583 occurring, and if I square root that, 7.65397 ... We'll round that to three significant figures, 7.65. That's it. How does it differ for a frequency table? Frequency table, exactly the same idea. We're going to use this formula here. So what we need the sum of the frequencies, which is just n. We need the sum of the x values, which is just the x value multiplied by how frequently it turns up. And then similarly, sum of the x squareds, so it's the x squared value, sorry, that one, x squared value multiplied by its frequency. Some of the frequencies then, we've got 2 plus 3 plus 3 plus 2. Slightly embarrassed now that I used a calculator. Some of the fx's, etc. Be careful. So we should have $133. And then for the sum of the x squareds, I'll write it out a bit more long-handed here. It's x squared multiplied by its frequency plus x squared multiplied by its frequency plus ... all the way up to the last x squared multiplied by its frequency. So we have 121 multiplied by 2 plus 13 squared multiplied by 3, 14 squared multiplied by 3, and 15 squared multiplied by 2. So the formula substitute in the values. Unintentional error. I'm not sure how to delete, so we'll just have to scribble. What I did there was put the sum of the x values, so this one, rather than the frequencies. And I want to subtract the mean squared, which is 133 over 10 squared. 13.3 would be perfectly all right under those circumstances. So we have 1787 divided by 10 minus 13.3 squared. I'm not a fan personally of the two different formulae. I like to think of it as basically the same calculation, but some of you might benefit from thinking of it as two different formulae. It depends on how your brain works. But your final answer there, 1.35. Okay? Finally, a group table. So finally, we've got a group table, exactly the same formula as the frequency table, because just like before, when you were calculating the mean, we used the midpoint as our x value. Now at this stage, I would strongly advise you pause the video and give this a go yourselves. Okay, so if we use our calculators to work out those values, so we've got 40 pieces of data, the total of all the x values, is 1,260. The total of all the x squared values is 74,400. And then we just substitute in. Bit less talking this time. So we've subbed in the numbers, used the calculator to work out the variance. Any trouble saying that? I'm just going to check that. Most sensible move is to have a natural display calculator and to type it in exactly as it looks like. Yep, and then square root that. Three significant figures. And there you go. Now there should be some practice questions in the same Moodle area for you to have a go yourselves. Okay?